in Pharmaceuticals in association with Higher Secondary Principals Forum.
A very good morning to all students. My name is Maria Xenia, physics teacher from St. Xavier's Higher Secondary School, Mapsa. Today, I just wanted to discuss with you a very important topic in physics. And that is, I've just showed some pictures. You can see the pictures. From that, you'll get an idea what is the topic about. The first picture shows some water, ripples. A drop is falling into the water. The second picture, there is a door opening. You can see something is entering into the door. So connecting these two, the first picture depicts about something what you studied in your 11th standard relating to waves. The second one is the one, as you open the door, it's a dark room. When you open the door, through the door, something is entering into the door, into the room. It is nothing, but it is the light. So connecting these two, we have the chapter Wave Optics or Wave Theory of Light. So in this chapter, we are going to study about the light in terms of waves. Now, as we know that many scientists were talking about light, it is an electromagnetic wave. You have studied about this electromagnetic wave in the previous chapters. And you have studied about the light also, another form, we call it as a ray optics. Now here, many scientists have a doubt how the light is transmitted from the source to another location. So how it is transmitted? So they were working about it. Finally, they found light has an energy. Because of energy, it is transmitted. Now, for example, when you see, I take a chalk. When I move the chalk, only I'm moving one end. The other end of the chalk is moving. It is due to all the particles are internally connected, which makes them to move. So therefore, when you consider, when one energy is transferred into the other, and it is progressive. So now I'm talking, in front of me the particles are there, which are vibrating, and they transmit the vibrations to the neighboring particles, which makes it to vibrate, and it is progressive. So with all these ideas in the mind, that is a very important thing we come to know about waves. So in 11th standard, we have studied about the waves leading to sound waves. Now the first one which I showed you example, you must have studied about the ripples which is formed in the water. Now when you consider here, in this case, the light is transmitted through it. So when you consider a very important thing over here, there are two types of waves we have seen in the sound. One is transverse, another one is longitudinal waves. So when the particles are moving, so when I threw a disturbance or stone into the still water, you can see some ripples which are in the concentric circles that have come from the disturbance. So what do you understand by a wave? A wave is a disturbance in a medium. Whenever there is a disturbance in the medium, a wave is formed. So here when you consider, so when the particles are vibrating, I'll just show over here, when the particles are vibrating, we can see some of them moving up and down over here. So when you connect all the particles over here, this forms a wave. So now when you consider the wave over here, particles are vibrating of different amplitudes over here. This is the one which forms a wave. So the wave has a projection, has a depression. The projection part of it, we call it as a crest. The depression part of it, we call it as trough. Now, this is the one, the main one, we call it as, this is a amplitude. This is one full wave which has a crest and a trough. A crest and a trough forms a wave. The length of one wave is said to be lambda. So, when you consider this, we have seen in the 11th standard. Now, when you consider over here how the light is propagating, where is the disturbance comes from? The disturbance is the energy of the electromagnetic wave. The energy is the disturbance which makes it to vibrate and travel in a medium. So when they are moving, how they move? When you consider there is a still water, when it disturbs, what is the disturbance forms over? Concentric circles. Now in the same way, when you consider, this is the one which we have seen in the ripples of water. Suppose when you take a string, one end of the string is attached to the fixed support. When you move the other end of the string, you can see a wave of this form. How can you say both different way? This is the top portion of the wave and this is the side view of the wave. So both is corresponding to one wave only. So when you see the upper portion of it, it looks like this. And when you see the sideways, the lateral portion, we say this is the wave. So these are the points where we have higher and lower. So when you consider, when I'm talking, the first particle is disturbed, it pushes the other particle, then it pushes its neighboring particle, and that particle pushes the neighboring particle, it goes on in the medium. In the same way, light, which is an energy, is also pushing one by one and it travels in the medium. So when you consider over here, so this is the one where we have continuous forms of wave. It is not the first one travels over, it goes here. By the time it reaches, this particle has reached here. So when it reaches here, it crosses an angle, and this is the angle we call it over. This is the one we can take it as 0. Here we take it as pi by 2. This one we take it as pi, and this is 3 pi by 2, and it is 2 pi. This is what these different points only, we call it as phase. So phase is the one, what is the angle from the origin it makes. From the starting point, what is the angle it makes over? That is what we call it as a phase. So when you consider the particles, many particles are vibrating. So here, this is the particle over here reaches to pi by 2. So now when you consider over here, suppose I consider in this way, so a part of this wave, it is progressive like this. Now when you consider this particle over here and this particle over here, they are at the same angle, just of 90. So now when you consider, they are in the same phase. Another way when you consider, this is also in the same phase. Now, this part of the wave, when you consider this part of only the upper part or the lower part, only one part of the wave, we call it as wavelets. That is known as wavelets. Okay. So now, even in the water, we have wavelets. Now, suppose when I draw a plane, okay, I would draw a plane or a straight line covering all the particles which are in the same phase. That is what is known as wave front. Okay, wavelet is a part of the wave and wave front is the envelope covering all the particles which are in the same state of vibration or which are in the same phase. Okay, so that is what we call it as wave front. Okay, so I'll just give you the, so this is the electromagnetic wave, light. So this light is an electromagnetic wave. You can see, because why we call it as electromagnetic wave? It is deflected by electric and magnetic fields. That's what we have different factors. I think we have studied in the chapter electromagnetic waves. Already you had a lecture relating to it. So all these factors, variations in both electric and magnetic fields occur simultaneously. They attain its maxima at minima at the same place at the same time. The direction of electric and magnetic fields are mutually perpendicular. They are perpendicular. You must have studied about it. When they are perpendicular, we call it as there is a velocity known as velocity selector, where they are perpendicular and equal. The force due to both will be equal. The speed of electromagnetic wave depends entirely on the electric and magnetic properties of the medium. It depends mainly upon the medium. How the medium is, then only they will progress in the medium. The main factor is the medium. So this we have studied already in the previous chapter. Okay. So light is a vector. Now here comes the wave front, which I said now. A wavelet is a point of disturbance due to propagation of light. A wavefront is the locus of points having the same phase of oscillation. As I said, see here, I showed over here, this is 90 degree, 90 degree. When I cover them with a line, it is said to be the, which is a wavefront. Now, when you consider a line perpendicular, suppose when I draw, say now, when I'm talking, I'll just give you a small example. I take a balloon, I just blow the balloon. When I blow the balloon, you can see it's slightly bulging out and out. Why? Because molecules goes inside and it pushes, compresses the molecules, and it is moving in front. That is what happens wave front. Wave, the particles are pushed in front. We don't consider the second particle because it pushes behind also. We consider only in the first one. I'll tell you later about it with an equation why we should not consider the back one. So it is pushing it forward. You can see the balloon is moving forward. Okay, when I blow, it moves forward, which shows the wave front. So in which direction it's moving? It's forward, moving front side. So that is what a ray. So when you see a light, it has got wave, it has got light. So it has both the properties. So light is the one. So here when you consider over there, it has ray. Ray is the direction of the wave in which it is progressive. The waves are progressive forward. That is the direction of the light. That is what a ray is. A ray is the direction of the wavefront. So in which direction they travel, that is what we call it as a ray. So this is a perpendicular one. It's always perpendicular to the wavefront. Now, what is a wavelet? Wavelet is a part of a wave, whether you consider the upper portion or the down portion. It is a spherical part of it, a part of a sphere. So therefore, when you consider, though it's a wavelet. Now, when you consider the wavelets, the covering of all the wavelets, when you draw them over there, the covering of all the wavelets is said to be a wavefront. Now, let us consider a source. Now, I'm going to talk about the source. What are the different types of source and what are the different types of wavefront we are going to study. Now, when you consider a point source, that means a dot, one source, the wavelets are emerging in all directions. That's what we call it as light always spreads. I showed you an example. When you open the door, when the light is entering into the all places, wherever it reaches, it can reach to. Even when you see at home, we have only one bulb. When you put the switch on, it spreads the waves to all parts of the room. It spreads out. Okay, so in the same way, whatever may be the source, the waves are spread in all directions equally. So when they are spread out over here, these are the ones spread out. So when I draw an envelope covering of all these wavelets, it forms a spherical wavefront. Okay, so that is what a spherical wavefront. So when you consider, like how we have seen in the case of ripples in water. In still water, if you disturb it with a stone, that's a disturbance. So when it is disturbed, it starts giving out the concentric circles of waves. Starting from the disturbance, there will be a smaller circle, bigger circle of increasing radius. So as the radius keeps on increasing over there, you have a smaller circle, bigger circles over there. In the same way over here, from the source, the waves are spreading out in a room, and from here we can see it forms concentric circles of concentric spherical wave fronts. Okay, so it is a spherical wave front. Now, even when you consider the water is disturbed by a stone, at the closer you can see a nice circle coming out. But when you keep on moving to the second circle, third one, fourth one, when you go at a distance from the center, from the disturbance, you cannot make out a circle. You can see only a part of a wave. That is what we call it as a plane wave. So wave front. Because what is a plane wave front? Where you cannot make out a sphere. It looks like a straight line. All the points comes in a straight line. So it looks like a plane wave front. Okay. So whenever we consider the wave front at a distance from the source, the same spherical part of it spreads out. At a distance, it looks like a plane, straight wave front. Suppose this is a point source. Second one, suppose if I choose a linear source, straight line. For example, we can see there are so many types of source, like we have a tube lights or any other LED which comes as a rectangular one. So when there is a linear source, it also spreads out the spherical wavelets in all directions which are equidistant from the source. So they are all equidistant. Again, if I draw an envelope covering of all this, it forms a cylindrical wavefront. Okay, so it forms a cylindrical wavefront. So when you consider the next part of the wave, because it spreads out, the second one is the second cylindrical wavefront. Then it forms another cylindrical wavefront, and it goes on and on like that. Okay, now in the same way, when you consider the cylindrical wavefront at a distance from the source, it also looks like a plane wavefront. Because we cannot get the full shape of it, only a part of it we get. So it looks like a plane wavefront. Okay, see here, this is from a point source how the waves are spreading out. Now I am showing in the blue color which represents the spherical wavefront. You can see the blue color one is the envelope covering all the spherical wavelets emerging from the point source. It is a spherical wavefront. Okay, so spherical wavefront from a point source. Now the next one I've explained to you about the linear source. It is a linear source. I said anything which is in rectangular form. Now from which the wavelets are emerging out. So when you consider here, this is the way they emerge out. So next is I am going to show the wave fronts. See here, which is in blue color, that represents a wave front. What are the types we have? It is a cylindrical wave front. Okay. Now here the directions are perpendicular to the wave front. Please keep it in your mind. It's very important to know about it. That's a concept. Whenever the waves are spreading, the direction of the wave spreading is the ray. It is the direction of the ray. That is the ray. Now here when you consider, and this ray is always perpendicular to the wave front. Okay, it's very important for the concept. Now this is a plane wave front, which I said when you consider the spherical wave front at a distance from the point source, or when you consider a cylindrical wave front at a distance from the source, it looks like a plane. We cannot make out the exact shape. That is what a plane wavefront. Okay. So, the pink dots which is wavelets, wavefront, red line is the one which shows the direction, that is the ray which is always perpendicular to the wavefront. Okay. So, I will move to the next one. So, spherical wavefront, when the source is the light, source of wavefront will be a spherical one. Point source means source of light is very small. That is why we consider it as a point object. Last year you must have studied about point object. For example, when you see, whenever I say point object, I tell the students an example. Suppose when you consider an aeroplane, in the airport, when you see the aeroplane, you can see what's the dimension of it, what's the length and breadth can be. But when it is flying high about it, you are not able to find out the dimension, because the distance of observation is greater than the dimension of the object. Then we say it's a point object. So, in the same way, when you consider the source is a point where it is very, very small. Okay. So, the source of light is a very small one. Okay. So, then ripples in water or in the form of concentric circles which are said to be the spherical wave fronts. Okay. Then I just said about the cylindrical wave front. When the source of disturbance is slit, we can choose even a slit. What is a slit? Is that you take a bulb from which the light rays are coming out. This was done by Newton. Beautifully he has done with a cardboard. He has taken 3 holes in the cardboard and just placed before the bulb. So, then he observed the light from the 3 dots, 3 circles are emerging out in a straight line. Then he said, okay, light travels in a straight line. That is what Newton has discovered first. So, then he said about the particles, all the corpuscular theory has come. Now, when you consider here, in the same way, wavefront is cylindrical. Over there, it spreads out. So, points are equidistant from the source. They lie on the surface of a cylinder. Then example, we can see when the rays of light fall on a lens. Okay. So, when it falls on a lens, I have just shown over here. Here you can see the light rays falls on a lens. Then you can see it is curved ones. Which are the curved ones over there? When they are falling on the lens, they are plane wave fronts. Okay. So, then it becomes curved. Okay. Out of the lens, it becomes a curved one. Because why? After refraction, they all converge, they all come closer. So, since all of them come closer, automatically the plane becomes a curve. Okay. So, that is the reason we consider here the plane wave fronts. After that we have spherical wave fronts, because that is the property of refraction. It is the process of bending the light rays. So, when it passes through the lens, it converges all the rays to a single point. So, since they all want to converge, automatically the plane converges, changes into the spherical shape. Okay. So, this is what we have. The next topic we have, it is because leading to this many scientists came about the discussion of the waves. So, one of the scientists, the first scientist who came about is Huygens principle we have. So, he has explained about what are the properties. Now, when you consider light, what are the properties we have seen in your earlier classes? Reflection, refraction, dispersion, scattering. All this we have studied about your rays. Okay, because we have 2 different parts we have. We are studying about the properties of rays, properties of waves. So, now properties of rays we have studied in the previous chapter. About what are the things we have seen? Reflection, refraction, spherical surface, lens maker's formula we have studied, and then dispersion, prism, refractive index of the prism we have seen, that we call it as a prism formula. Then we have seen about the optical instruments, astronomical telescope, and then we have studied about simple microscope, compound microscope. All these are the properties of rays. What is the properties of rays? They travel in a straight line. So when you consider they travel in a straight line, these are the properties. Now, because light is an electromagnetic wave, it has the ray as well as light wave, both are together. So now ray we have studied in the previous chapter. In this chapter we are going to study about the waves. But Huygens said, using the property of waves also, I can prove it obeys the laws of reflection and the laws of refraction. So first of all, let me say, what is Huygens' principle? Now, when you consider a source, from the source, the wavelets are emerging out in all possible directions. So now, S is a source from which the waves are emerging out. I have taken a point source from which the waves are coming out. He says that each point on the source acts as a source of secondary wavelets. Now, when you consider over here, first of all, here this is source, secondary wavelets are emerging. So, what I have to do next? I have to draw an envelope. An envelope is the one, a tangent, a common tangent to all the spherical parts of the wave. When I draw a common tangent to all the spherical parts of the wave, that is the wavefront. So whenever we consider a tangent to it, it is always perpendicular. Okay, it is always perpendicular to it. So now this is the wavefront. This wavefront, we call it as a primary wavefront. The first wavefront formed from the source S. That we call it as a primary wavefront. This primary wavefront, he said, each wavefront acts as the source. So it looks like as if the bulb from here, it shifted here. The bulb, whatever we have the source, it can be a bulb or candle or a slit, anything. It looks like as if they are shifted over here and from which the waves are emerging. With the same intensity, there is no difference at all. So when you consider here, this is the one wavelets emerging from this, and an envelope covering of all this is the one secondary wavefront. Because the first one is the primary, from which the source is coming out. It gives out the secondary wavelets, and when it covers all the secondary wavelets, it becomes another wavefront that we call it as a secondary wavefront. Okay, again, so this becomes like a source. They start giving out the secondary wavelets, and this becomes a, and when I cover all this, that becomes a tertiary wavefront. Like that, a large number of wavefronts are formed. Each wavefront acts as the source. I am the source. I am the bulb which gives out the light radiation. So like that, there is no change in the intensity of light. So what do you infer from it? So a wavefront is the one, each wavefront is the one which are in the same phase, which has the same frequency, which are in the same point of vibration, that we call it as locus of points. Okay, so I'll just give out, that is what given out as the principle, Huygens' principle. Okay, S is the source which gives out the wavelets over here. So here these are the ones, because the direction is the ray and the circle is the one wavefront. Okay, so here we can see they are spherical waves. Now listen here students, there are something, the circle is from the dots, circle is in front, a part of a circle is in front, back also. We consider only the forwarding one. Okay, so now here you can see I covered that one with the blue line, which is a wavefront. That's a primary wavefront. And the second one I showed it in dots. Why? I'll tell you at the end of this explanation. Now, then it acts as the source and it proceeds over here. So that is the new wavefront, spherical. We call it as primary wavefront. Okay. So now it progressive. It moves forward. And therefore here, when it moves at a distance, you can see at a distance, it is the plane wave front. It forms a plane wave front. That's what I said. Because at a distance, you're not able to see the entire circle. You'll see only a part of a circle which looks like a stray. So this is a plane wave front. They are also progressive in this way. The front one we call it as we make it as a straight one, and the back side we put it as a dotted ones. Okay. So this is a new wave front, and that is a plane which is at a distance from the source. Okay. So now the red dots on the wave front over. Now this is what he has given us the principle. Each point on a wave front acts as a fresh source, as if it is a source. I am the one giving the light, so no change in the intensity. Okay, this is what it is over here. The new wave front at any time later obtained by taking the forward envelope. Envelope means covering of all the secondary wavelets at that time. So backward front is rejected, because I told you here, this dotted ones in the blue are rejected. Why? Because that is a particular equation we have. Where we have the equation, the intensity is given by the formula, which is proportional to half 1 plus cos theta. Now when you consider the backward direction, it is 180. So it is 180. Obviously for backward direction, it is 180 angle. So cos of 180 is -1. So 1 minus 1 becomes 0. That is the reason we don't consider the backward, which is in the light blue one. We don't consider that. Okay. It is a very important application question which we normally give it in my college always. Why it is not considered? Why the backward wavefront is not considered? Okay. So this is what the Huygens principle over. Now, here he has proved with the laws of reflection on a plane surface. Okay. Consider a plane wavefront. What is a plane wavefront? I said from a point shows the wave. Okay. When you consider at a distance a plane wavefront. So consider a plane wavefront incident on a surface. Now, here the plane wavefront is coming over. So when they are reaching to the surface, A will reach first. A will reach first. Okay. So this is the reach first. When it reaches the surface, plane made a surface, here this reach, the point B reaches over here, whereas point C reaches over little smaller distance over there. Now A reaches first. As soon as it reaches by Huygens principle, each one acts as a source. It strikes the surface that separates air medium. This is one medium, air medium, and this is the mirror. Whenever anything falls in the mirror, what happens? It undergoes the process of reflection. So here, by Huygens principle, it starts giving out the secondary wavelets. So these secondary wavelets, it reaches to a distance over here. It reaches to some place. When the point B reaches over here, A has reached to some distance over here. Okay. From A, the wave has reached over here. By the time point B reaches the surface, and that time C has reached to this point over here. Okay. C is now here. Now after B has reached, it starts giving out the secondary wavelets. So they travel until the last point of C reaches the surface. The point B reaches, it starts giving out the secondary wavelets. These secondary wavelets travel the same time until the last point of the wavefront reaches the surface. Okay, now C is here, B is here. Now this is the one. These are the wavelets which are reflected, which are sent back over here. Now the covering of all the wavelets, it forms the wavefront. And this wavefront, we call it as a reflected wavefront. This is known as reflected wavefront. And this is the one, we call it as incident wavefront. Okay, so this is the one of incident over here. This is the incident. Now, when you consider when a ray of light is falling on a surface, there is a normal drawn and the angle between the incident wave and the normal is said to be angle of incidence. In the same way, this surface is the normal. The angle between the incident wave, this is the incident wave, right? And this angle is said to be angle of incidence I. That is said to be the angle of incident I. Now, here the waves are emerging. This is the waves are emerging in this way. So, this is the reflected wavefront. And I'll number this over here as PQ. Okay, I'll just take it as PQ. Now, when you consider over here, these are the ones which is coming over. And now, the time taken, so when A has reached here, C is at this point, okay, at this point. We're able to see over here, this is the point it has reached when A has strikes the surface. So that time, the time taken from here to here, let T be the time taken, during the same time, this A is giving out the secondary wavelets. So the secondary wavelets are emerging over here. So when you consider over here the time taken by the wave, so when you consider here the time taken by the wave to reach from A to P, and here I'll take this as C dash, B dash. The time taken from A to P and the time taken from C to C dash is the same time. Okay. So, for the last point to reach the surface, it says I am not waiting over, I just travel a small distance. It travels because by Huygens principle, each point on the source acts as a source of secondary wavelets. So, they travel over here. So, this is the one wave we have. So, these are all the reflected ones. The covering, we call it as a reflected wave front. Now, when you consider over here, what is how the wavefronts are drawn? It is a tangent drawn to the spherical wavelets. So, the angle is 90. So, this angle is 90 degrees. So, when you consider over, this is the one of a reflected A, P, C. Okay, C dash. A, P, C dash. This is the one. So, this angle between the reflected wavefront and the normal, we call it as angle of reflection. And this angle is 90 degree. Okay. So, when you consider over here, at this point over here, this is the one we have in this case. Now, here there is another one also we have. This is the one angle of incidence over here. Now, when you consider over the different types of it, okay. So, there is one we consider over in this way. That is the angle of incident wavefront, and that is the reflected wavefront. I will just draw a little bit clearly so that you will understand over there. So, XY is a surface. This is a plane mirror. Okay. So, when a ray of light is incident, the reflected waves over here, it travels the covering. This is the one, it's a reflected wavefront. This is A, B, C. This I will take it as B dash, C dash. Okay. So, I will show all the reflected ones in the blue color. This angle is 90 degree. This angle is 90 degree. The time taken for C to C dash is T. The time taken for A to P is taken over as time taken is T. So, this is the same time taken over. So, now when you consider the triangles, two different triangles I am going to consider. One triangle is the one where we consider here, first triangle over here, which is ACC dash. ACC dash. First I will consider the triangle ACC dash. This angle is I, this angle is 90 because this is angle of incidence. This is the angle of reflection. Now, when you consider the triangle ACC dash, what is this is 90 degree. AC dash is a hypotenuse. What is the value of sine I? Equal to opposite side, which is CC dash, upon, when you consider over here, by adjacent side AC. Okay, CC dash upon AC. Now, actually when you consider over here, this I will come little later about this sine I. Before that, I will just tell you about the two different triangles. So, when you consider the triangle over here, this is also APC dash. So, these are the two triangles we have. This angle is 90 degree, okay, and this angle is not known, and this angle is angle of reflection R. Now, when you consider the two triangles, since the time taken for C to C dash is T, during the same time it travels a distance AP, same time. Now, when you consider as they are in the same medium, the incident and the reflected are in the same medium. So, therefore, when you consider here the incident wave, the reflected, same medium. So, if they are the same medium, A medium, let V be the velocity of the wave. Velocity of the light wave, we take it as 3 into 10 raised to 8 meter per second. So, V is the velocity of light. So, what is the distance travelled by it? AP equal to, that is why we take it over. We know that velocity is equal to distance upon time, or distance is equal to velocity into time. So, therefore, when you consider the distance AP equal to velocity into time, if V is the velocity of wave in the first medium and T is the time taken, AP is VT. Similarly, when you consider the wave from A to B, here during the same time it reaches to C dash. So, the distance CC dash also equal to VT, because velocity into time, same velocity, same time. So, when you consider, since both of them has the same value, we say that AP is equal to CC dash. Both the distances are equal. So, when you consider the triangle AP equal to CC dash, AP equal to CC dash, and then this angle C is common, angle C equal to angle C equal to angle P, which is equal to 90 degree. Angle C equal to angle P, which is equal to 90 degree. And then what we have over here is that since these two are equal, now and this is the triangle, when you consider the triangle ACC dash, and when you consider the triangle APC dash, both of them have the same common side. Which is the common side? AC dash, AC dash. Okay. So, therefore, these two triangles are congruent. Because why? Because this angle 90 and CC dash equal to AP, and AC dash is the common side for both the triangles. So, both the triangles are congruent. So, here when you consider over here, but okay, so therefore by specificity, this angle equal to this angle. By specificity, angle I equal to angle R. This proves the first laws of reflection, which states that the laws of reflection states that angle incidence is equal to angle reflection. Now, please look into this. This is the one angle incident wavefront, reflected wavefront. Okay, this is the normal drawn over. Angle of incidence, angle of reflection, CD reflected wavefront. Okay, reflecting surface, C with a C So this is what I have stated over. Time is equal to distance traveled, because the same time I have taken over. So I have done it over here in this way. Actually I have taken a sin A, sin A. I said not necessary for us. We will go directly into the distance. So actually this is a little higher form of it. You can just take it of the second part of the wave. It is AC sin A, AF sin I minus sin A. That's the form over here. So this is the way we explained over there. For the rays of light from different parts of the incident wavefront, the values of AF are different, but light from the different points of the incident wavefront should take the same time to reach the corresponding points of the reflected wavefront. So it should not depend on AF. So therefore sin A upon sin R becomes 0. So we take it over angle I equal to angle R. So this is another method of it. Okay. So this is what the proves the laws of reflection. Now what are the things we have seen now? Wavelets, wavefronts, and Huygens principle. And Huygens principle prove the laws of reflection. The next we have over here, using Huygens principle to prove the laws of refraction. The next we have laws of refraction at a plane surface. Now when you consider a refraction, whenever a ray of light passes from one medium to another medium, it suffers a bending in its path. So that is what we have here, refraction, and we are going to prove the laws of refraction. In order to prove the laws of refraction, we need two different media. So here when you consider over here, I am just going to consider a surface XY that separates two media. One is a one rarer medium, I will choose it as an air medium. Second one, any denser medium, it can be water, glass, any surface. So when a ray of light enter into this, okay, it suffers a bending in its path. You can see, okay, it is due to the process of refraction. So it bends over there. So I'll just draw a line over there. This is a plane wavefront. So when I draw the plane wavefront over the AB is a plane wavefront. So when you consider the point B, we have 90 degree. Why? Because it is a tangent drawn to your spherical wavelet. So then over here, these are the spherical wavelets which are traveling in the second medium. So when I draw a tangent covering all the secondary wavelets in the denser medium, it forms the refracted wavefront. Okay. So that is the refracted wavefront. The angle between, I drew a normal at the point of incidence. The angle between, that's the one way we have over here. This is the angle of incidence. I drew a normal perpendicular to the surface. So that moment when you consider the angle between the normal to the incident, it becomes the angle of incident. Okay, incidence. So in the same way over here, when you draw a normal, so here angle BAC, which is the one we have here, angle BAC is also equal to angle I. So now when you consider over here, this is the refracted wavefront in the second medium. Angle R is the angle between the normal and the refracted wavefront, the angle of refraction. So let mu1 be that is refractive index of the first medium, and mu2 is the refractive index of the second medium. Okay. So here when you consider over in the same way, now when the point A reaches the surface, the last point of the plane wavefront is at B. For B to reach to C, A travels a distance d, AD. But AD and BC will not be the same, will not be of the same length. The time is the same. The time taken for B to reach C and the time taken for A to reach D is the same. But the distance is not the same. Why? Because of two different densities. The velocity of the wave is different for different medium. So therefore, as the velocity differs, Because when you consider denser medium, all the particles are closer. So it cannot travel freely in the denser medium. It travels little slow. So therefore, it covers the short distance in the same interval of time AD. But BC is a longer distance travel because it is a rarer medium. So therefore, when you consider BC, the time taken for B to reach C, the time taken for E to F, all are the same. So same time F to G, same time A to D. So now I am just taking it over towards the AB is the incident wavefront, CD is the refracted wavefront. Now C is the speed of light, T is the time taken by light to go from B to A, B to C or A to D. Now listen here. Time taken T is equal to the same time, that is the time here is taken over the time taken E F plus F G. Okay. So what is the time taken? Distance traveled is during the time, same time it travels from E to F and F to G. So what is the distances over here? EF upon C. When you consider the time taken is distance upon the velocity, Fg upon the velocity over here. And therefore we have here, how will you consider them? Okay. Now when you consider the triangle over here, this is AEF. Okay, I have just considered the triangle AEF. Now when you consider this angle is 90, this angle is 90, this angle is I. Now when you consider this triangle, sine I is equal to opposite side upon hypotenuse, because this is 90. So where we have EF upon AF. So what is the value of AF? Here, what is the value of EF is equal to AF into sine I. So because when you consider over here, this is AEF and this is 90, this is I. Sine I equal to opposite side, which is EF upon hypotenuse, which is AF. So what is EF is equal to? AF sine I. Okay. So this is what I have written over here. In place of EF, I have written AF sine I upon C. In the same way, when you consider over FG, for FG, we consider, now I am going to consider the next triangle over here, which is in the second medium, where we have like this, where we have here F, C and this is G. Now when you consider this angle is R over here and this angle is equal to 90. Now what is the value of sine R is equal to FG, opposite side upon hypotenuse, which is FC. Okay. Now what is the value of FG? FG equal to FC sine R. So this is what I have written over here. So EF is AF sine I, FG is FC sine R. Okay. Now I'll move to the next one. So when we consider over again, AF is equal to, we take the difference of those two over here, which is AC sine I upon this. So we can just simplify this factor and then we should not depend upon the AF. So this is possible when you consider sine I upon C minus sine R upon V equal to 0. This is not possible over. So we take only this. The rays of light from different parts of the incident wavefront, the values of AF are different. So we consider only this. It doesn't depend upon F. So this is possible only if this is a condition. So we have here sine I upon C minus sine R. So let us equate now. So after this step, since it is equal to 0, we equate sine I upon C minus sine R upon V equal to 0. Or when we consider sine I upon C equal to sine R upon V. Cross multiply here, take this over here, sine I upon sine R equal to C upon V. This is nothing but over here. C upon V is the ratio of two velocities in two different media. These two ratios of velocities is the one we call it as refractive index. Okay, so therefore mu equal to sin I upon sin R, which proves the laws of refraction. That is said to be Snell's law. Okay, so this is what we have over here. We take it over mu. Okay, so this is what we have over here. Okay, mu is equal to sin I upon sin R. Okay, so this is the way. So though they have the property of waves, we have proved the laws of reflection and laws of refraction. Okay, so with this I'll stop today. I'll continue the rest in my next class. Thank you, students.
Prudent Scholars, powered by Lupin Pharmaceuticals.
अब आपकी सुरक्षा आपके हाथों में। ल्यूपी सेफ हैंड सैनिटाइजर, आपका और चेन्नई सुपर किंग्स का फर्स्ट लाइन ऑफ डिफेंस। अब आपकी सुरक्षा आपके हाथों में। ल्यूपी सेफ हैंड सैनिटाइजर, आपका और चेन्नई सुपर किंग्स का फर्स्ट लाइन ऑफ डिफेंस। अब आपकी सुरक्षा आपके हाथों में। ल्यूपी सेफ हैंड सैनिटाइजर, आपका और चेन्नई सुपर किंग्स का फर्स्ट लाइन ऑफ डिफेंस।